Okay, so the next thing that we need to work on is three-dimensional elements. So far, we've started off with two-dimensional or one-dimensional elements with bars and beams. We moved on to two-dimensional elements that we called shells or plate elements. And then now moving up an additional dimension, we have three-dimensional elements. I have several, I think 4 different types of three-dimensional elements. We mentioned the axisymmetric elements that represent 3D shapes, but those are two-dimensional elements still. Okay? These are now fully three-dimensional elements that can be modeling things that don't have any symmetry, that have irregular shapes that we can't simplify down into something simpler. Okay, so my point early on was if I have a cantilever beam, I should probably use a beam element to represent that. A one-dimensional element that only has length. Okay, it's not worth spending the time to define all the geometry when the cross-section is constant down its length. Okay? In several of our assignments, we have used the tapered beam as an example of using these different element types and seeing how the results come out. Okay? If my beam is tapered, I was trying to draw that kind of as an isometric view kind of thing. If my tapered beam is constant thickness, and in a top view it is tapered, then this is a really good candidate for a two-dimensional element type, because I can capture the taper with my two-dimensional element, but my thickness is constant. And so I don't really need to model that third dimension. So shell elements would be ideal for this. Let's say now, though, that my tapered beam is tapering in the vertical direction as well. So just to keep something simple. So now I have a tapered beam that is different thicknesses as well as different widths down its length. I'm not going to be able to capture that with shell elements because my thickness is different in different areas of my model, and so I can't use two-dimensional elements. So this I would have to go to a three-dimensional element. So obviously, as the geometry gets more complex, we eventually have to start using three-dimensional elements. We try to avoid it because three-dimensional elements means more degrees of freedom. And more degrees of freedom means longer times to mesh it, longer times to analyze it, and then in some cases, not as good a results. A lot of times on three-dimensional analyses, you're not going to get exact results, which means I need to continue to refine the mesh to get closer and closer to the correct values. So, the simplest three-dimensional element is a constant strain tetrahedron. It has 4 nodes. Tetrahedron looks like this. It's a triangular shaped pyramid. Okay, this is not the pyramids of Egypt because the pyramids of Egypt have a square base, right? This has a triangular base, but it's a pyramid made up of triangles. There is 4 nodes. Each node has 3 degrees of freedom. So translations in the X, Y, and Z direction. 3 degrees of freedom times 4 nodes gives us 12 total degrees of freedom for each element. Okay, notice on our three-dimensional elements, they do not have rotational degrees of freedoms at the nodes. They only have translational degrees of freedom. Okay? If you remember back to when we talked two-dimensional elements, we said that we had triangles were constant strain triangles, and we said that they were kind of bad when we had to deal with bending. Well, this is the three-dimensional analogy to constant strain triangles, which means that they're not going to give really good results in bending or torsion. In SolidWorks, you can specify draft quality mesh, and if you're using three-dimensional elements and you choose draft quality, it's going to use constant strain tetrahedrals to calculate it. What you need to be careful about then is if you're doing a bending problem, your results are not going to be as good. Okay? So the way to specify a constant strain tetrahedron in SolidWorks is to use draft mesh. It's a quality setting when you do your analysis. A better result is if we use linear strain tetrahedrons. These have additional nodes at the midpoint of each side. So notice we have the nodes at the corners, and then we have additional nodes on each side of between the corners. If I count all those up, it ends up with 10. Each one has 3 degrees of freedom like before, so 10 times 3 is 30. So I'm going from 12 degrees of freedom to 30 degrees of freedom. The advantage is then I get a better result for my outputs. My displacements are going to be better, and my stresses are going to be better. In SolidWorks, if you choose a high quality mesh, then you are using linear strain tetrahedrons in the analysis. Okay? Like I've said several times, SolidWorks hides some of this stuff behind settings so that you don't get confused as to what is a linear strain tetrahedron versus a constant strain tetrahedron. But what it is doing in the background is changing the element type in order to get you better results. In assignment 7 here, I think I asked, for problem number 1, I said use the draft quality to do the tapered beam again, and then use the high quality. And you should get different results for the two. And your high quality should be much closer to the real answer than your draft quality is. Okay, so I wanted to show you that. So you'll have to set that up for assignment 7 for problem 1. We also have sides that are element shapes that are rectangular. SolidWorks does not have this, but if you use software like ANSYS, you can specify hexahedrons, which are brick shapes, often referred to as brick 8, and then brick 20. Okay, same concept, except we're using rectangular sides to our shapes. We end up with 8 nodes on the brick 8, and 8 times 3 is 24 degrees of freedom. It's going to be a little bit too stiff because the sides remain straight, so a better result gives you a brick 20, which has the mid-side nodes. Count all those up, I end up with 20 nodes, so 60 degrees of freedom, and I'm going to get a little better results. But like I said, SolidWorks does not have these element types. You'll only run into these if you use more advanced modeling packages like ANSYS. Okay? All right, so we already talked about draft quality versus high quality. For the types of models that we're doing that are relatively small, why not specify high quality all the time? You're going to get better results. But as you get into more and more complicated geometry, greater numbers of elements, you're going to notice a big time difference between using the draft quality and the high quality. And so if it's sitting there and the computer seems to be bogging down, you just want some quick results, then you can specify the draft quality and you'll get a much faster solution. For our assignments, we're talking minutes at the most for most of these analyses. The time problem doesn't really become an issue. But like I said, when I used to work in industry, it was not unusual to have a computer crunching away for hours on a model. And that's really, really frustrating to sit there and wait a couple hours for it to spit out an answer and then discover you didn't put the constraints in correctly or something like that. So the purpose of having the draft quality is to speed it up so that you can get a quick result. And then once you're happy with the way it's modeled and you want a better result, then you can run it again with the high quality mesh. Okay? All right, you have control over the mesh. And in both assignment 6 And assignment 7, it says you need to show that you have refined your mesh sufficiently to make sure the results are good. So that means not using just the default settings for your mesh. You need to find out where the high stressed areas are, and then you need to go and reduce the mesh size in those areas. And so SolidWorks has the ability where you can apply local control. You can pick a point or an edge of your model, and you can say, I want to specify the element size, and you can specify the element growth ratio. And what that does is it refines and makes the mesh much smaller in the areas that you're interested in. Okay, I couldn't remember if I had a picture of that or not. Okay, so if this is my model, and I find that I have some high stresses in certain areas of the model, I would like for the mesh to be smaller in the areas of high stress. Okay? This one is showing the way you can set different areas, so it's not exactly what I wanted. But if you pick a point, then it's going to have smaller meshes around the point. If you pick an edge, then it will reduce the mesh along the edges. If you pick a surface or a face, it's going to have smaller mesh sizes along all of that face. Or if you pick a component, then it's going to make the mesh smaller for the entire component. Okay, that's what that graphic is showing. What I was wanting to show is maybe something like, let's say I have a structure that has a hole in it. So let's just keep things nice and simple, just a cantilever beam, and I have a hole drilled in my cantilever beam. Where is the high stresses going to be? Okay. So I'm going to get some high stresses that are up here, and I'm going to get some high stresses that are down here because of that hole. Combination of, we've got a reduction in the cross-sectional material. There's less material there. And then we also have the effect that you guys learned in 211 of stress concentration factors, right? Or we could do, same thing. We could do, a beam that has a notch in it. We're going to get some really high stresses around the corner of that notch because of that notch being there. Okay? So, when I want to improve my results, I could just tell it, make it all the elements in the entire thing smaller. Remember, SolidWorks is a N-type refinement. So it increases the number of elements, or it makes each element smaller in order to improve the results. I can do that, but the drawback is I'm making really small elements down here at the corner where the stresses are practically zero. And so I'm going to greatly increase the amount of time that it takes to analyze this model, and I'm not going to get any benefit out of that. So this mesh control concept allows us to reduce the element size in the areas where I know the stresses are going to be high, but leave them big over in the areas where it's really low anyway, and I don't care what it is. Okay, so that's the point of doing this. You want to refine the mesh in the areas where there's high. So what typically the process is done is that you do an analysis, you look and you see where our stress is high, and then you reduce the mesh size in that area, and then go and solve it again. Okay, so it's kind of an iterative process as you work towards the results, the final results you get for the problem. Okay, so you have that ability to control that. You'll have to start doing that in assignments 6 and 7 to improve your results. Use them on the other, some of you guys haven't done some of the other assignments, you can use them in those places too if you want to. There's also some checks in there, some different settings that you guys can take advantage of. One of them is aspect ratio checks. Element results are always going to be better the closer my element sizes are to consistent geometry or consistent aspect ratios through the geometry. Okay? So for my tetrahedral, the closer each side of that triangle gets to be in the same, the better the results are going to be for that element because of the way the math works. Okay? For bricks, the closer each of those are to a cube, the better the results are going to be. And so the software does some element ratio checks. I'm just telling you this because so you know that kind of stuff is going on in the background. We're looking for tetrahedrals that have similar proportions on all the dimensions versus something that looks like this. And there are limits in the software that it will kick out and say it cannot mesh it if it can't get away from some of these settings. So when you are setting your mesh control and setting up things like the element growth ratio, you can set it so that you get some really crazy, horrible looking elements by the way you set those, you change those values. And sometimes it'll kick it back out and say cannot mesh this because you've specified poor values for those changes in geometry. Okay? So thinking about that, if I want to reduce the element size here, my triangles can't all be exactly aspect ratios of 1 because I have to transition in geometry. I have to get smaller and smaller, right? Okay, really simple looking at that. If I'm just using rectangular elements and I want to get to a smaller rectangular element, if I'm not using mid-side nodes, I can't do it that way. Okay? These have to, my elements have to start getting warped in order to make that transition. Because the corners have to stay the same. And so then I get an element that's not square. Or it starts getting elongated. It gets skewed and it gets elongated as I make that transition. Okay? So there are checks in there, and if you get an error about that, that's what's going on, is that you've got really bad aspect ratios, and so SolidWorks is going to warn you that you're going to have problems with your results. Jacobian check is another check that is used, and this is for the parabolic type elements, so the linear stream tetrahedron. It's looking for severely distorted elements. So because I have the mid-side nodes, you can get elements that have really curved sides. It tries to avoid distorting them too much, and so that's what the Jacobian check is, to make sure that they don't get distorted too much either. All right, and I've talked about this with a few people, but I had another question about it, so I put it in here to make sure that you're aware of it. Some of these assignments, you are going to need to find the value of stress or the value of displacement at a particular point. And the tool that allows you to do that easily in SolidWorks is the probe tool. Okay? So why might I need this? Well, let's say we're looking at a problem. Let's just go back to this cantilever beam with a hole in the middle. If I want to check my stress values to my hand calculations, if I do just a simple calculation, MC over I, stress is equal to MC over I, and I use the whole length of this beam and the moment that is over here at the edge, my MC over I equation is going to tell me the stress that should be up here, right? Okay? But if I do this problem in SolidWorks and I get the numbers and the colors, the value that's up here at the top is going to be the highest value of stress, right? Right? Okay? And if the highest value of stress is over here, how do I compare that to my MC over I equation? Well, I can't. Okay? So I need to use the probe tool to probe what is the stress over here so I can compare that stress to my hand calculation. So that happens a lot. You'll have a stress concentrator in there somewhere. Your hand calculation might not include that stress concentrator. So probe some known place where you know where the stress is, and then compare those values. Okay, that's a pretty useful tool. And I think that'll become more obvious as we go through these problems, that you can't just use the max value that SolidWorks puts on the graph, because that max value might not be something you're very interested in. You might be interested in particular other locations on the structure. So like I said, comparing your hand calculation to your SolidWorks gets hard because you need to make sure you're comparing the right number in SolidWorks to your hand calculation. It's not always just whatever this max number is. Okay? All right, I think that was it for this slide, this PowerPoint too. Okay, any questions about any of that? Okay, so that is the material then that will show up on the test next week. So you're going to need to go back through all this material, get as much of these assignments done as you can. I will be available next week. I'm just not going to be in town. So shoot me an email if we need to set up a WebEx meeting. We can do that. Talk to you on the phone. We can go back and forth via email, however is most convenient to you. But we got to get on this and get some of this done so we can finish this up this semester. Anything else?